Hello everyone, this is Rudree Pathak from Department of Pharmaceutical Technology, LG Institute of Pharmacy, Ahmedabad. Today we are starting with our first chapter of Physical Pharmacy, B.Pharm Semester 3, that is States of Matter. Now you must be knowing that due to current pandemic situation, we are still not able to resume our classes at the campus. But till that time duration, our studies should not be hampered. So we are going to begin with our sessions with the first chapter of Physical Pharmacy, that is States of Matter, from today. Now I would like to request you to kindly subscribe our YouTube channel, that is Pharma Ignite, for further notifications, and you should not miss out anything important that is going on. Thank you so much. Let's begin with our session. Now, before we begin with our first chapter, that is States of Matter, we need to talk about what is actually physical pharmacy and why it is scheduled in B.Pharm Semester 3. Now, if we talk about the subjects of pharmaceutics that we have studied so far, in Semester 1, we talked about pharmaceutics, that is dosage forms. In Semester 2, we talked about pharmaceutical engineering, that is equipments needed for preparation of those dosage forms. Now in Semester 3, we are shifting to the physical aspects of those drugs or excipients that are actually needed for preparation of dosage forms. Now study of these physical aspects is actually physical pharmacy. That is what we are going to talk about in this semester. Now we are going to focus on what are the three basic states of matter and what are two other states of matter which are less explored, but still it is there in your curriculum. So let's begin with our states of matter chapter. Okay, so let's begin with our chapter on states of matter. Now, how many basic states of matter do we already know? We know about solids, we know about liquids, and we know about gases. Now in case of solids, there will be close packed arrangement of atoms, ions and molecules, and which also shows that there will be very strong attractive forces between them. Now in case of liquids, the attractive forces will decrease a little bit and the arrangement will be a bit haphazard. In case of gases, the electrostatic forces of interaction decreases like anything, and there won't be practically any arrangement of atoms, ions and molecules. Now if there is a change in state from solid to liquid, we call it as melting or liquefying, and the reverse of that is known as freezing. If the state of matter changes from liquid to gas, we say it is a boiling state, and the reverse of that is known as condensing. Now there are some solids which actually convert directly from solids to gases, and this is known as sublimation. Example is camphor, kapoor. If we keep camphor at room temperature just like that, then after some time duration we may observe that it is converted into a gaseous state directly. There is an opposite situation as well, and that is known as deposition, where the gaseous state is converted directly into solids. So in nutshell, we'll be having three basic steps or three basic states of matter: solids, liquids and gases. Now there is a twist in the story. There are two mesophases also which exist between solids and liquids. That is a transition state. And there is mesophase number 2 which exists between a liquid and a gas as well. Obviously, we are going to talk about that in our later lectures. Now, let's begin with our first state of matter, the simplest state of matter, and that is solids. And in solids, we are going to talk about the crystalline state, where the arrangement is kind of regular between atoms, ions and molecules. Now basically in solids we have two states, crystalline state and amorphous state, but today we are going to talk about crystalline state. Now crystalline and amorphous will differ in the physical properties, physical pharmacy. They are going to differ in their physical properties. Now, the arrangement of atoms, ions, and molecules is actually the most critical part in crystalline state and amorphous state. As you can see in the diagram, the arrangement of the building blocks is quite regular. In case of amorphous, the arrangement is there, but it is not regular. Some books also refer amorphous state as super cooled liquid. You need to remember this term. Now, crystalline solids will have a specific set of properties. They will be having regular arrangement of atoms, ions, and molecules. They will be having a definite shape because of this regularity in that arrangement. They are practically not compressible or incompressible, and they have shown, or they will be showing, a definite melting point. There will be a fixed range in which they will be converted into a liquid state. Now, what is crystallization? How crystallization is actually taking place? Now, if we talk about crystallization, you need to remember two terms: saturation and supersaturation. Now, what is saturation? Imagine you are having a glass of water and you are adding sodium chloride to that. You keep on adding till a specific point, till the amount of liquid which is present in that glass, it is capable of taking that salt. Now, this state where maximum amount of salt is already added, that is known as saturation. You get saturated. Now, if you heat that glass of water, what will happen? The capacity of water is going to change. I'm sure you must have done this before. Now, this change in capacity will lead to excess of salt addition in that glass of water, and this phase is known as supersaturation. So, if you increase the capacity of a liquid and if you keep on adding salt to that, then that is known as supersaturation. Now, if you cool down that glass of water, the excess of salt will crystallize out. Crystallization, that's your term. Now, this crystallization is actually affected by a list of factors, that is type of solvent that you are using. If you are using water, the crystallization will change. If for the same solid you are using alcohol, the crystallization is going to change. The temperature at which you are heating the liquid, the temperature at which you are cooling down the same liquid, that is going to affect. The pressure at which the entire procedure is carried out, that is going to affect the crystallization process, and the crystal yield, that is how much amount of crystals are actually you are taking out from that solution. And also the salt present. What is the principal salt? Say for example, if you are carrying out crystallization for copper sulfate, and other than copper sulfate, if any other crystal is also present in that liquid, then that is going to affect the crystallization process. Now, what are the arrangement of these repeating blocks, that is atoms, ions, and molecules? They are going to give a definite shape to the crystals. And now, if we talk about a cubical shape, then the example for that is sodium chloride. You must have learned about this in your school time, where sodium ions and chloride ions are actually arranged in the type of a cube, in a shape of a cube. Now, next example is tetragonal. The arrangement actually is evident with urea. Then hexagonal, the arrangement is actually seen in iodine molecules. Then monoclinic and triclinic respectively. Now, these are the arrangement or the ways in which building blocks are actually arranged to give an overall structure to the crystal. Now, what are the building blocks of these crystals? If we talk about three basic building blocks, then these are ions, molecules, and atoms. If we talk about sodium chloride, we have classical example of sodium chloride. The arrangement of Na plus and Cl minus, it gives rise to a cubical structure. True, but what are the building blocks? What gives rise to that cubical structure? The building blocks is ion. It is Na plus and Cl negative, which gives rise to a cubical structure. And what are the bonding force between these structures? It is electrostatic forces of attraction between Na plus and Cl minus, that is cation and anion. Now in case of, say for example, carbon dioxide or naphthalene, the building block can be termed as molecules. It is the molecule of CO2. It is the molecule of naphthalene which is holding the structure together. Now if we talk about the holding forces or binding forces, it can be termed as van der Waals forces of attraction or hydrogen bonding. Now this is weaker than the electrostatic forces of attraction. So you can imagine the structure is also going to change. In case of cube or NaCl or in that kind of structure, the holding forces are stronger, so the structure or the melting point will be different. In case of carbon dioxide, solid carbon dioxide or naphthalene, the holding forces are a little bit weaker, so obviously the melting point range is going to change again. Now there is the third category, that is atoms. In case of diamond and graphite, the building blocks are atoms and they are held together by covalent forces of attraction. So you can see as the building blocks are changing, the holding forces are also changing. Okay guys, we are still talking about crystalline structure. Crystalline structure can have a definite shape depending on the building blocks which are actually making them. Now as you can see in the bottom of the slide, I have noted down a definition, and that is a metallic crystal. Now what is a metallic crystal? As goes with the definition, they are actually a crystalline structure where positively charged material or ions are actually surrounded by a free cloud of electrons. It is not a simple electron, there will be a cloud arrangement around the positive charges. Now because of such an arrangement of metallic crystal, they make them a good conductor of electricity, because the electronic arrangement is not fixed, they are vibrating, and they will be then considered as a good conductor of electricity. We are going to talk about this in detail in our later lectures. Now we are coming to the end of the lecture. Why end of the lecture? Because we have so far talked about the crystalline lattice or crystalline structure. Now we need to compare that crystalline structure with the amorphous structure, which is totally opposite of what we have discussed so far. In case of crystalline structure, we talked about fixed arrangement of atoms, ions and molecules, giving it a specific shape, making them incompressible, having a definite melting point, having a definite heat of fusion, and that is what making them considerable for a specific set of physical properties. Now in case of amorphous solids, everything is happening in opposite. They are not having a geometrical shape, not fixed geometrical shape. They will melt over a wide range of temperature. They are not going to show a peak of melting point, and they are compressible, and they will not have a definite heat of fusion. Now I want you to remember this chart. I want to take a picture of this chart, because in next lecture we are going to start over from this slide. We are going to start with this comparison. We are going to revise with this comparison. We are also going to talk about the last point in the slide, that what is anisotropic and isotropic. So that's all for today's session. Thank you for your patient hearing. I would like to recommend you again that please subscribe the Pharma Ignite YouTube channel. It is going to keep you updated with the latest thing that is going on with our campus. And I would like to also request you to have a quick revision of this lecture before we begin with our next session. Thank you so much.